So consider this problem where you have a joint PDF of x and y to be is given to be half x e raised to minus x for x greater than y greater than 0 and 0 otherwise. So the joint PDF is good in this region. This is x, this is y, so this is where x is greater than y. You have this function. And z is given to be the product, and w is going to be the quotient. So the problem is to find the joint PDF of the product and the quotient, and then from there get the marginals, etc. So let's look at this problem. Notice that x and y are positive. Moreover, x is greater than 1. So right away we see that w is greater than 1 because x is greater than y. And z is positive because x and y are positive. So z is where the joint density function is valid for z positive and w greater than 1. And now to see the next is to figure out the roots. So from here x1 is wy from here, and that when you substitute it here for x1, this gives you z equal to wy squared, or that gives us y is square root of z over w, and there's only one positive root because x and y are positive and in this region. That's y1, and x1 is going to be, when you substitute for this y1 here, you get x1 to be square root of zw. So we got the two roots. We got the one pair of roots. So this is step one, figuring out where the region going to be. Figured out the roots. Then the Jacobian, which is either way we can find out. Let's say dc by dx, dc by dy, dw by dx, dw by dy. So that's going to be here dc by dx is y, dc by dy is x, dw by dx is 1 over y, dw by dy is minus x over y squared. So this, if you do, you get y cancel, so x over y minus 2x over y. So the absolute value of the Jacobian is 2 times x over y, but x over y is given to be w, so that's 2w, and w is positive, so I don't need, in fact it is greater than 1. So we are ready to substitute for the find out the joint density function of CW. That's going to be 1 over the Jacobian. There's only one root here, and if xy, x1 comma y1, so that's 1 over 2w, and x1 comma y1 is simply x1 e to the power minus x1. There's a half here, so x1 we figured out to be square root of zw. So square root of zw, so this will turn out to be 1 over 4 z over w e to the power minus square root of zw for z positive, w greater than 1. So that's the joint density function. So that's going to be in this region for z positive and w greater than 1. So it's this region. So notice that the rectangular open infinite region, that being the case, let's find out FCC. So that's w is greater than 1. So w need to be integrated out. FCW c comma w dw. So that's this is going to be a function of z. So square root of z over 4 integral 1 over square root of w e raised to zw w. So I'm going to substitute the obvious one, CW, to be U. This gives us square root of Z over 2W dW to be du. Remember, U is CW. So so if I substitute here, so notice dW is going to be, from here you get dW is 2 square root of W over du. So I'm going to substitute that here. So this gives us FCC equal to square root of Z over 4. W goes from 1 to infinity. And when so here when W is 1, this is square root of Z to infinity, and 1 over square root of W. So also you have 1 over square root of W, then 2 square root of W over, so a lot of cancellations. And e raised to u, so you simply get half e raised to minus u over minus 1. So the answer turns out to be half e raised to minus z, or z positive. And if you quickly do integration, that's a valid density function. E raised to minus square root of z for z positive. This is not exponential, but something something which decays exponentially. So that's the density function of z. And to figure out the density function of w, we can take the joint density function and integrate out z. And the joint density function was 1 over 4 square root of z over w e to the power minus zw dc this time. So again, we'll use the same thing. Zw I'm going to put to v, but this time the derivative is with respect to z. So that's square root of w over 2 square root of z. dz will be dv. And so if I substitute for dc from here, dc would be 2 square root of z over square root of w dv. So let me substitute it here. So the limits are 0 to infinity here. So we get fww. And the limits still stays the same. So 0 to w. And I have 1 over 4 square root of z over w. And then dc, instead of dc, I'm going to have 2 square root of z over square root of w e to the power minus v dv. So notice that I have, this turns out to be a 2 cancel, so I have half integral 0 to infinity. I have here z over w. And then if I multiply by w here, this becomes w squared, and the cw is the variable v. So I can write this as half w squared 0 to infinity and this CW becomes, notice here, square root of CW is V, so this is V squared e raised to minus V dV. But this whole thing is, if you integrate, you get 2. So this 2 and 2 cancels, and you get the answer to be 1 over W squared for W greater than 1. So something like this. And this you can quickly see, 1 over W squared dW is minus 1 over W, 1 to infinity is 1. So that's a density function. But the product of these two, this together with this, is not equal to what we started with. So they are, Z and W are not independent. They are dependent random variables. So what is interesting here is, even though the region where the joint density function is non-zero is rectangular, infinite rectangular, nevertheless CW are dependent. So that's the problem, figuring out the joint density function and the marginals. So joint density function is this, marginal of Z is here, and so notice Z is like an exponential looking functions. It's not even square root of an exponential, but exponential looking function. And this is 1 over inverse quadratic. And that's the problem.